So, good evening, everyone. So, we will be discussing the assignment 8 of the electrical machines 1 course. So, here, what all we will be discussing. So, let me write. So, today we will be seeing the basic, what you say, lap winding, wave winding, like how many number of parallel paths, all these things we will cover. Okay, how many number of parallel paths are there in both the windings. Okay, and other things also we will discuss. Then we will see the EMF equation. Then we will see the various kinds of DC machines. So DC machines, there are various kinds. So they are like separately excited, self-excited. Now in self-excited, we have series, shunt. Okay. So we will be covering these things. So let us start. So first of all, we will see the, so I'll write on this side the lap winding. And on this side, I will write wave winding. Okay. So number of parallel paths. So the number of parallel paths for the lap winding is equal to the number of poles. Okay. And number of parallel paths for the wave winding is 2. Okay. Then number of brushes. Number of brushes is also equal to the number of parallel paths or number of poles for the lap winding. And for the wave winding, it is 2. Then here, what else is there? Then number of commutator segments. For both the cases, it is equal to the number of coils. Okay. So you see, it is something like this, that let us suppose we have a question that let number of conductors Z equals to 8. Okay. And P number of poles equals to 4 for a machine. Okay. For simplex lap winding connected machine. Then it is reconnected. Is reconnected as simplex wave. Okay. So let us see how these things happen. So first of all, the number of parallel paths we denote by letter A. Okay. So this number, this A denotes the number of parallel paths. Okay. Now here for the lap winding, the number of parallel paths is equal to the number of poles, which is 4. Okay. Now for wave winding, we know that it is 2. So wave winding A is equal to 2, which is the parallel paths. Okay. Now, how many number of conductors per parallel path? So number of conductors per parallel path. So this is number of conductors per parallel path. So this is how much? So this is total number of conductors are 8 and here the parallel paths are 4. So it is 2. Now here what is the case? So this is 8 by 2 which is 4. So how will this be looking like? So it will look like this. Okay. So let me draw it with the other color. So this is the conductors. Okay. Now this is one parallel path having two conductors. Then another parallel path having another two conductors. Like this. Okay. So you can see that, wait a second, let this person join. So you can see here that I have drawn 4 parallel paths for the lap winding, which is equal to the number of poles. And here for there are total number of conductors are 8. So in each of the parallel paths, there are 2 conductors. Okay, so I have drawn that. Similarly, for the wave winding, how it will happen? So there has to be 4 conductors per parallel path, and the parallel paths are 2. Okay, so these are the 2 parallel paths. Now there are 4 conductors. 2, 3, 4, 3, 4. Okay. So now let us suppose that each of these conductors carry 1 volt. Okay. So let us say in the question it is mentioned that the voltage across each conductor is 1 volt and it can carry maximum, it can 1 ampere current. So let us see what happens in the two cases for the power and the voltage. Okay. So you see this. So in the series part, the maximum current which can flow is 1 ampere, right? So here the 1 ampere will flow. Here 1 ampere will flow. 1 ampere will flow. 1 ampere will flow. So at the output, the total current you will see is, because these are parallel connected, so all the currents will be added up and you will get the total current as 4 ampere. Okay. Now here the this parallel path will carry 1 ampere. This parallel path will carry 1 ampere, so that because you see we cannot take 2 ampere here because all of these conductors are series connected in this path and their maximum current rating is 1 ampere. Okay, so we in this path there will be 1 ampere in this series connected path, and in this series connected path there will be 1 ampere. Okay, so maximum there will be 2 ampere. Now let us see about the voltage. So let me take some other color. So let us say, so here we will see 1 volt. Here we will see 1 volt. And because this is parallel connected, so here also 1 volt, 1 volt. So in the parallel part, we will get 2 volt. Okay. Now here, what is the situation? This is 1 volt, 1 volt, 1, 1. So here you will see 4 volt. Okay. So let us see what is the situation of the load current, what is the situation of the here load current, voltage VL, power and resistance. Okay, so you see current rating is proportional to number of parallel paths. Okay, so current is proportional to parallel paths and voltage rating is inversely proportional to number of parallel paths. We can see that in the case of the lap winding, the parallel paths increases, so the voltage rating became 2 volt. But here the parallel paths are 2 only, so there is more voltage. Okay, so it is inversely proportional to number of parallel paths. So this is inversely proportional. Okay, now what about the power? You will see in both the cases the power will be same. You see 4 into 2 8 watt, and here also 4 into 2 8 watt. So in both the lap winding and wave winding, the power remains to be same. Okay, so someone may ask you that what will be the change in this question. The question can be that what will be the change in the voltage, current, and power ratings. Okay, so someone may ask that what is the change when this lap winding is reconnected as wave winding. So what will happen to the voltage rating? What will happen to the power rating? What will happen to the current rating? Okay, so let me write it. So here, so IL means lap, okay, and IW means wave. So IL by IW is equal to AL by AW, because it is directly proportional to the parallel paths, right? So current in lap winding divided by current in wave winding is directly proportional to the parallel path in the lap winding and parallel path in the wave winding. Now, what about this? This is inversely proportional, the voltage ratings. Okay. So you know that if someone asks you if there is a wave connected system, then you are connecting it back to the lap connected system. So what will happen to the voltage ratings? What will happen to the current ratings? But the power in both the cases remains the same. Okay. So you see here, so lap winding has more current rating and wave winding has more voltage rating. We have seen from this example, right? So these are the things. So I hope you will remember this. You remember this chart. Okay, this chart is very important. Now we will see about the number of coils. Okay, so let us see this. So in some questions, it will be asked that the number of coils will be given to you, and then it will be asked what are the number of conductors. Okay, so you see in a single turn coil, there are two conductors. So it is like this. So this is a single turn of a coil. So a coil is like this. Now in this coil, where are the conductors? So the conductors are here. Okay. So this is one set of conductor. This is another set of conductor. Okay. So there are two conductors. So the number of conductors, or Z, will be equal to 2 times the number of coils. Like for knowing this number of number of conductors per parallel path, and for doing all this, you need to know the number of total conductors, right? Sometimes the information is given in terms of number of coils. Okay, so in that case, how to do it? Now, number of conductors in a multi-turn coil. So here what happens that it is like this. Okay, so here you have suppose 2 turns. Let us suppose this is 1 turn. So let us see about the 2 turn. Now in a 2 turn conductor, it will be something like this. Okay, okay, so like this there are 2 turns. Now here, so what about the number of conductors? So the number of conductors in this case, here there is one conductor in one of the sides. Then here it is, then on each of these sides. So here we have. So here the number of conductors Z is equal to 2 into T, where T is the number of turns, okay, into number of coils, okay. So you remembered this also. In some of the questions, this information the number of conductors information will be given in terms of number of coils, okay. So you have to remember this. So here the T is the number of turns. Okay. So let me write it also. So where T is equal to number of turns. Okay. Now let us see the EMF equation. So in the professor's lecture, the EMF equation has been derived. Okay, I'm not deriving the EMF equation. I'm just writing the formula. Okay, directly. So the formula for the EMF is ZNP phi by 60A. Okay, so I'll write what all these things are. So this is number of conductors. Okay, so N is the speed in RPM. Remember. Okay. Then P is number of poles. Phi is flux per pole. And A we know is the number of parallel paths. Okay. So this is very important. Most of the questions are like based on this equation only. Okay. Now we will see some of the DC machines and how their connection are like separately excited, the series, self-excited series connected, shunt connected, all these we will see, okay? And how to write the equations. So let me write. So classification based on the method of excitation, okay? So classification of DC machine based on excitation. So we have DC generator. So we know this is separately excited. And another one is self-excited. Now in self-excited, we have shunt, we have series, and then we have something known as compound. Okay. Now in compound also, we have long shunt, and then we have short shunt. Okay. And then in long shunt, we have differentially compounded and differentially compounded, and then we have cumulatively compounded. Cumulatively compounded. Similarly, here also we have the same two categories, differentially compounded and then you have here also cumulatively compounded. Compounded. Okay. So now let us start with the separately excited DC generator. So So I will be discussing today this, and this. Compound long and short shunt is not in this week. So I'll maybe discuss it in the next week. Okay. So I'll today, in today's class, I'll be discussing these four. Okay. So separately excited DC generator. So here what happens that you have a field winding which is given a separate DC voltage. Okay. So this is given a separate DC voltage. Okay. Now here you have the armature. Okay. So let us suppose this back EMF is EG. Okay. So here everywhere if I'm writing so EG will be this voltage. Okay. So this is back EMF or generated voltage. So this is generated voltage. Okay. So this is EG. Then let us suppose that there is some small armature resistance drop, and then this is the current IA, which is armature current. So, and let us suppose this is voltage V. So this V is terminal voltage. So in questions, you will be asked that find terminal voltage for a separately excited machine, find terminal voltage for a shunt generator, or find terminal voltage for a series generator. So terminal voltage is here. Okay. Then IA is the armature current. RA is the armature resistance. And EG is the generated voltage. So what is the terminal voltage? As if we apply the KVL, so we will get terminal voltage as EG minus IA RA. And what about the load current IL? So the load current IL is in this case equal to armature current. Okay. So for separately excited machine, this is how you write it. Okay. So now here, if you see that we need a separate DC voltage for excitation purpose, and you can see that the field winding is here and the armature winding is here. Okay. So they're electrically isolated. So for this machine, so I'm writing just extra things here. So here number one is that the field and armature windings are electrically isolated. And another thing is that the field excitation, okay, field excitation is independent of IL and V variations. Okay. So it does not depend on the terminal voltage variation. It does not depend on the load current variations. Okay. So it is independent of the load variations and terminal voltage variations. This EMF or this basically this I mean to say this field excitation. Okay. The flux will be constant in this case. So flux does not depend on V and IL. Okay, so this is important point. Now we will see the shunt generator. Okay, so let us see the shunt generator. So a shunt generator is something like this, that you have the generated voltage here. Then here we have load. And then here only we have the field winding. Okay, now let me draw the armature resistance. So RA is here. So let me draw it clearly. Okay, so this is RA. And let us suppose this shunt winding is having resistance RSH. So let us suppose this current is ISH here. This is IL and this is the armature current. Okay, this voltage across the load is V. So what are the equations? So you see that the field winding is it actually has high resistance. Okay, so you will see that the field winding of a shunt generator has high resistance to handle low current ISH. ISH is generally low. Okay, so here, so let me write it here. So for this case, it is like the terminal voltage for this case. So let me first write the equations. So V is equal to EG minus IA RA. Okay, this is not changed, but you see the armature current consists of two parts. It consists of ISH, it also consists of load current. Okay, so you see here the armature current was only load current, but here it consists of two parts. Okay, and what about I shunt? I shunt is V by R shunt. Okay, and hence the flux is proportional to I shunt, which is proportional to V. Okay, so this is important. In the previous case, the flux was independent of V and IL, but here the flux is proportional to terminal voltage V. So that is why this terminal voltage act as the excitation, and hence it is called as voltage operated field. So terminal voltage acts as excitation. Excitation means field excitation. Okay, and hence it is called as voltage operated field. Okay, now we will see the series generator. Okay, so in the series generator, so let me draw it again. So series generator. Okay, so here we have EG. Here we have RA, and then we have a field winding. Let us suppose this is R series. Okay, and then we have load connected. So this is load. Okay, so here this is current IL, this is V, this is IA. Okay, so first of all we can see that IA is equal to I series, which is also equal to load current. So the current, which is the armature current, is also the load current, and it is also flowing through the field. Okay, now what about V? V is EG minus IA into RA plus R series. Okay, and here we can see that the flux is proportional to I series, which is proportional to IA. Okay, so that is why this is this previous one was a voltage operated field. So this one is a current operated field. Okay, so this was a voltage operated field. This one is a current operated field. Okay. So that is all I wanted to discuss. Now, in the case of motor, what will happen is, so I will just draw one case of motor. So let us suppose I draw the, for this only, let me draw the motor case. So for the motor, for a series motor, what will happen that here you will have EB, you have RA, because it is the same machine, series connected machine. Okay. Now here you have B. So here because for a motor, it takes the, what you say, voltage to rotate, right? So the current, so basically it is given a power so that it rotates. So the current is in this direction. Okay. So current is in this direction means, so what about the EB? EB is B minus IA RA plus R series. And here also flux is proportional to I series, which is proportional to I. So you can see that the, what you say, KVL changes in the case of motor because the current direction changes. So what happens is that the terminal voltage V, the applied voltage V is more than the back EMF EB. Okay, like that. Similarly for the shunt motor also, so let me draw the shunt motor. So for the shunt motor, let us first erase these things. Okay. So here, let us have a shunt motor. So here, this is EB, this is RA. So this is the current direction. This is this direction. This is this direction. Okay. So here you see your IA is equal to IL minus ISH. Okay. And then what about the, so here we have voltage V. So what about EB? EB is V minus IA RL. Okay. So these are the equations. And here also your ISH is equal to V by RSH. Okay. So you see the direction of current changes from the term, what you say, the where it is connected. So here it is not the load, it is basically your some DC voltage. Okay, some power which is getting supplied by some voltage source. So here, let me draw this. Okay, like this. Okay, so this is about the motors and the generators. For separately excited also, you can do it in the similar way as the series motor. Only this R series part will not be there. Okay, so that is the thing. Now we will see the questions one by one, and if there is something to be discussed regarding that question, then we will discuss in that question. Okay, so let us see the question. So you can see these things, right? Is it clear whatever I have discussed till now? Yes, ma'am. Okay, if there is doubt, so you can ask. Okay, if there is anytime any doubt in the things which I have discussed, you ask. Okay, so let us see the questions one by one. So here, let us see the first question. Now in the first question, this is the data which is common for the two questions. Okay, now in this data, what they have given, that it is a 4-pole DC shunt generator which is having 1000 lap connected conductors with each conductor having 0.012 ohm resistance. So and also the generator is charging a 130-volt battery with negligible internal resistance. When the so the speed is 1224 rpm, then the charging current is 7.5 ampere, and when the speed is 1332 rpm, then the charging current is 23.5 ampere. What we have to find is, we have to estimate flux per pole. Okay, so how to do it? So first of all, let us write down all the things. Okay, so first of all, Z is given as 1000, Z is the total number of conductors. Okay. Then what about the number of parallel paths? It is equal to the number of poles, which is 4. So this is 4. Now what about number of conductors per parallel path? Which is Z by A. So this comes out to be 1000 by 4. So there are how many conductors? So there are 250 conductors in each of the parallel paths. Like how in this question we had, if you see this thing, here we had Z, like 2 conductors per parallel path for the lap winding. Here we are having 250 such conductors. Okay. So it is like this. So here I have, so this I'm representing the whole 250 number of conductors. Okay, so this is 250. Then here we have 250. Then here we have another 250. And then we have 250. Okay. Now it is said that each conductor is having 0.012 ohm resistance. Now, indirectly, they are telling you that, because you see, what is armature resistance? In all these cases, the RA, which is the armature resistance, what is armature resistance? Armature resistance is due to these conductors. Okay. You see, these conductors are having some resistances. So, because of which there is RA. Okay. So, indirectly, by giving you the, what is the resistance of conductors, they're telling you to calculate the armature resistance value. Okay, so let us calculate now. 250, and then they're saying that each of the conductor is having 0.012 ohms. So what will happen? So in this path there will be 250 into 0.012 ohms. So in this part there will be 250 into 0.012 ohms. In this part there will be 0.012, and in this part also there will be 0.012 ohms. Okay, so what will happen to the total combination? So because these are parallel connected, so Z total, let us suppose this is Z1, Z2, Z3, Z4. So Z total, or basically I mean to say R, because this is armature. So let us write it as R only. Okay, otherwise there will be confusion. So this is R1, R2, R3, R4. Okay. Now, what about RA? RA is nothing but R1 parallel to R2, parallel to R3, parallel to R4. Okay, so this is the armature resistance. Because why there is an armature resistance? It is because of these conductors which are there, either they are lap connected or wave connected, but there are coils which are having conductors, and these coils have some resistance in it, due to which there is armature resistance. Okay, so now indirectly we are supposed to find the armature resistance using this information. So we know that the parallel combination of this will be like 1 by RA will be 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4. Now all of these 4 parallel path resistances are same. So it becomes 4 by R1. So RA becomes R1 by 4, which is 250 into 0.012 by 4. So this much is the armature resistance. Okay, so if you calculate, it will come out to be 0.75 ohms. Okay, now they are saying that when there is a speed change from 1224 rpm to 1332 rpm, there is this much of current change. Okay, so what is the speed change? So N1 is 1224 rpm. Current I1 is 7.5 ampere. Then N2 becomes 1332 rpm, and the current I2 becomes 23.5 ampere. Okay, so what is the change in the current? So the change in speed N1 minus N2, which is delta N, change in speed is 108 rpm, And due to this change in speed, what is the change in the current? So the change in current is 23.5 minus 7.5. You are saying something? हाँ 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 हाँ, तो इस तरह से 16 एम्पियर. ओके, so this will be 16 ampere. Now, so what is the, so basically what is the, because see, in both the cases what will happen is, so what will be the change in the EMF? So the change in EMF will be equal to this current into the armature resistance RA. Okay, so it will be delta I into RA. So RA we have calculated, so this is 12 volt. Okay, so this is the change. Now what is the EMF? So we know that the EMF equation is ZNP 5 by 60A. Now here del, हाँ बोलो. हाँ हाँ, 16 into 0.75 किया, यही. ठीक है. So now what I'm trying to do, I have to find flux per pole, phi, right? Now I have calculated delta E. Now what is this delta E? Delta E is Z into delta N P phi by 60A. Okay, so here we have number of conductors. Here we have delta N also. So delta N is here 108 RPM. Delta E we have calculated here. Okay, from this information. So we have delta N, we have number of conductors, we have number of poles, and we know the parallel number of parallel paths for the what you say lap connected winding. Okay, so all of this information is known. We can find out phi. Okay, so let me write it in a clear page, these things, because here everything is messy, right? So 1 minute, let me write it here. So here it was like this, that we have 4 parallel paths. Okay, R1, R2, R3, R4. So RA is R1 parallel to R2, parallel R3, R4. Now, yes. Now, what is the resistance of this parallel path? So, first of all, we have to find number of conductors per parallel path for that. So, it came out to be 1000 by 4, because there are total number of conductors 1000 and number of poles are 4. So, the total number of conductors per parallel path are 250. Now, for each of the conductor, each conductor resistance is 0.012 ohms. So 250 conductor resistance will be how much? 0.12. Yes. So this is the thing. Now this is for all the paths. So this is for R1, this is for R2, this is for R3, this is for R4. Now what is RA? RA is R1 by 4 because of the parallel combination. Okay. So this will be 250 into 0.012 by 4. So this is 0.75 ohms. Now the change in speed for which there is a change of current is, so N1 minus N2 or delta N is equal to 1332 minus 1224, which is 108 RPM, and I1 minus I2, which is delta I, is equal to 23.5 minus 7.5, which is 16 ampere. Okay. So what is the change in the EMF? So change in EMF is delta I into RA. So which is 16 into 0.75, which is 12 volt. Okay. Now delta E is what? Z delta N P phi by 60A. So total number of conductors are 1000. Delta N we have find it in RPM as 108. Number of poles are 4. 5 we have to find. 60 is this, and number of parallel paths for the lap connected winding is also equal to number of poles, which is 4. Okay, and this is 12 volt. So from this you can find flux per pole. So 12 into 60 into 4 by into 4. So you can calculate this. Okay, so if you calculate this, you will get it as 6.66 milliweber. Okay, so here 4 gets cancelled. Here you can do this. I'm not doing it. Okay, this comes out to be 6.66 milliweber. Okay. Okay. Now let us go to the. Is there any doubt in this question? Is there what about others except Sambit? Is there any doubt? Shiv Kumar Mahato, is there any doubt here in this question? Okay, so if you have doubt, so please stop me in between and then I'll clear it. Okay. Now let us go to the next question. Now in this next question, we have to estimate the field resistance. Okay, so how we will estimate the field resistance? So first of all, it is said that this we found from the previous question that for delta N, the delta E corresponding delta E was 12 volt. So for 108 RPM, we had 12 volt. Okay, so here 108 RPM corresponds to 12 volt. So how much will 1224 RPM correspond to? How much EMF it will be? So it will be like this, that 12 by 108, which will be for 1 RPM. Now 1224 RPM, it will be 12 by 108 into so this will be this much volts. Okay, so you will get it as 136 volt. Now 136 volt is the EG. Okay, because we are relating it to that generated EMF, right? Because the speed here in this formula, we are using the generated EMF formula, right? So here this is the generated EMF, not the terminal voltage. Now it is said that the generator is connected to a 130 volt battery. So the terminal voltage V is 130 volt. Okay. So it is like this, that you have this is a shunt generator. Okay. So this also is very important. So shunt generator means that here you have a field winding. Here this is the back EMF part. Okay. Here we have armature resistance. So this is RA. This is RSH, and here it is connected to a battery. Now this battery is 130 volt. Here we have found that this EG is 136 volt. Okay. Now what we need to find, and you said that this is the charging current is 7.5 amperes. Okay. So charging current is 7.5 amperes. So here this charging current for this battery here is 7.5 amperes. Okay. न, नहीं नहीं ISH इधर है, ठीक है, ISH इधर है. ये जो चार्जिंग करंट का जो बात हो रहा है, चार्जिंग करंट किसके लिए? बैटरी जो लोड है उसके लिए. ठीक है, तो ये बेसिकली बोल रहे लोड करंट इतना है. चार्जिंग, ये जनरेटर का चार्जिंग नहीं बोल रहे. ठीक है, सो दे आर सेइंग जनरेटर चार्जेस अ 130 वोल्ट बैटरी. ठीक है, और चार्जिंग करंट मतलब बोले चार्ज कर रहा है जनरेटर एक बैटरी को, एंड इट्स चार्जिंग करंट इज दिस मच. ओके, so they are telling that this load current is 7.5 ampere. Okay, this is basically they are telling us charging current. ठीक है, now here what we need to find, if we can find IA, then we can find, using the IA information we can find ISH. So what is IA? IA is nothing but EG minus V by RA. ठीक है, so EG is what? 136 minus V 130, and RA we have found from the previous question. Okay, so this comes out to be 8 ampere. Okay, now we know that I shunt is nothing but IA minus IL. So this is 8 minus 7.5. So this comes out to be 0.5 ampere. Okay, so shunt current in general is a very low current, as I have written also here, that you see field winding of a shunt generator has high resistance to handle low current. Okay, so this 0.5 is a low current, right? So that is the thing. Now here let us find out the field resistance. So for finding the field resistance, what we have V by RSH. Now RSH is nothing but V by ISH. Now what is your terminal voltage V? Because you see this is the voltage which is also getting applied here. Okay. So that is why your ISH is nothing but V by RSH. But in the question, we are supposed to find field circuit resistance. We know the terminal voltage as 130 and we know that shunt current from the previous calculation. So we get this as 260 ohms. Okay. Is there any doubt here, Sambit and Shiv Kumar Mahato? Okay. So now let us go to the next question. Now in the next question, they are saying a 125 volt separately excited DC generator with armature resistance 0.3 ohm is first run at 810 RPM. Okay. The open circuit voltage is set to 140 volt by adjusting field current. So it is like this. Okay. So here this is the separately excited generator. So 1 minute. So here we have a separately excited generator. So this is RA. Now RA is how much? 0.3 ohms. Okay. And here it is said that this voltage, this EG, open circuit voltage means that when there is no current flowing. Open circuit means when there is IL is not flowing. So what is the terminal voltage? So terminal voltage, if IL is not flowing, IL is 0. Okay. IL not flowing means IL is 0, not that. Okay. So in that case, what will happen? This output or open circuit voltage will be equal to EG. Okay. So they are saying that initially it is set so that it becomes 140 volt at 810 RPM. Okay. Now it is said that when the load current is 58 ampere, so in that situation, the what you say the this speed drops to 750 RPM. Okay. So they are telling you to find what is the V in this case, in the second case. So let us first find this. So we know that this generated voltage is ZNP5 by 60A. So here EG is proportional to speed and it is proportional to phi. Okay. Now phi in this case is not dependent on, we have seen it is not dependent on load current. It is not dependent on the terminal voltage. So phi in the two cases, when the speed is 750 RPM and when the speed is 810 RPM, it remains the same. So EG is proportional to N. So EG1 by EG2 is equal to N1 by N2. Okay. So EG1 was 140 volt. So EG1, this is EG1 and this is N1. This is N2. Okay. So EG2 will come out to be EG1 N2 by N1. Okay. So this is EG1 is how much? 140 volt into 750 by 810. Okay. So this will be something like 129.6 volt. Okay. So this is EG2. Now what we have to find? We have to find V2. So what is V2? It is nothing but EG2 minus IA2 into RA. So this IL is also equal to IA2 because it is series. Okay. So V2 will be nothing but 129.6 minus 58 into 0.3. Okay, so this will be 2.2 volt. Okay, is there any doubt in this question? Okay, so this is how you can find the terminal voltage, okay, for the second case. Now we go to the next question. Now in these things, what you need to know is, you need to know that what things are constant and what thing depends on what. So anytime you see a question like suppose DC shunt generator, you draw this circuit, okay, in the side somewhere you draw this circuit and label these things so that you can quickly write the EMF equations, you can quickly write, you can quickly imagine it, okay. So you can write these equations very quickly and just see what all things are available to you and use it, okay. Here also you draw this circuit quickly so that you will know, okay, phi is remains the same in the two cases, okay. So what to use, okay. So always quickly draw a small circuit, okay, it will help you in the exam. Now let us go to the next question. Actually, I have not discussed the theory for this. So here they're asking you that this is a two-pole machine and they're saying it is a 720 RPM DC generator, and they're saying 102 lap connected coils, all this. But they're asking you that the flux density is given to you, and they're saying each pole shoe spans 120-degree mechanical, armature length is this much, diameter is this much. So what you need to find, so first of all in this question, let us find flux per pole, okay. So the information given is B average, okay. B average is given to you, length is given to you, diameter of the rotor is given to you, okay. So it is like this, so this looks like this. So this is a two-pole machine. So let me draw a two-pole machine. So if suppose these two-pole machines were covering the whole 360-degree mechanical, so if suppose it was like this, so this is one pole and suppose this is the other pole. So in this case, the flux we know is what? We know flux is flux density into area. B average into area. So this is flux. Okay. Now let us see for one pole. Let us see, because we are calculating flux per pole, not the whole flux, right? Flux per pole. So what is the area of this? So first of all, we need to have a length. So you see what is the length? So we know that the whole circumference of a circle, okay, which is having a diameter D, is how much? We know that this circumference is pi d. Okay, now this pi d into the length will give me the area of the whole what is a rotor. But we want the what you say area per pole. So area per pole means this total 360 degrees getting equally divided into the two poles. So this will be nothing but pi dl by number of poles, p. Okay. So this is the area A. So flux will be B average into A normally, okay. But if they're telling you something like, because you see this is total 360-degree mechanical, but out of this 360-degree, here I have assumed that 180 degrees across one pole and 180 degrees across the other pole. But here in this question, they're telling you something like this. आर्मेचर देखो, आर्मेचर लेंथ जो है, दिस इज डायमीटर इज गिवन ना, तो डायमीटर जो है वो डायमीटर तुम्हारा ये डायमीटर है, और आर्मेचर लेंथ कैसे, क्योंकि आर्मेचर देखो ऐसे दिखता है ना, ये यहाँ पे ऐसे होता है और इसके यहाँ अंदर में ये सब पोल्स और ये सब रहता है, ठीक है। लेकिन ये लेंथ तो यहाँ रहता है, तुम समझ रहे हो, ये साइड व्यू है, ठीक है। तो ये ऐसा चीज है, तो हम लोग ये एरिया तो यहाँ निकाला, क्योंकि फ्लक्स कैसे ट्रेवल करेगा, फ्लक्स तो पूरा ऐसे जा करके फिर ऐसे आएगा ना, समझ रहे हो। तो इसीलिए हम लोग को ये एरिया जब लेना है तो वी हैव टू टेक दिस एरिया, बेसिकली दिस एरिया विच इज गेटिंग कट perpendicular to the flux. So you will see that that area, ये length जो होगा, this length is this length, okay, and diameter is the diameter will be given, diameter of rotor, diameter of armature, something like that, okay. Now here you see in this question I have assumed that this is 180-degree mechanical for each two poles, okay. So I am assume I have considered that this the degrees are three for the two poles. It is like depending on the number of poles, that the mechanical degrees equally getting divided. But here they are saying that instead of making it a full circle, this is 122-degree. Okay, so they are saying that each pole shoe spans for 122-degree mechanical. Okay, now here I have found that there is one mistake here actually in this calculation. Okay, but I will clear whether this is a mistake or something, but I think this is a mistake. Okay, so what is flux per pole? हाँ हाँ, 360 डिग्री तो दो के लिए है, 360 डिग्री is for the two. Okay, but they're saying, they're not saying that both the pole shoe spans 122-degree, right? They're saying each pole shoe spans for 122-degree. But if we see here, so okay, I understand. Okay, no, it is correct only. Okay, it's not a mistake. Okay, it is correct. So let me just erase this. This is correct only. Okay. So this is the situation. Now here you see, if this were, if so here the formula for flux per pole is B average into area. Now area is what? It is pi dl into degrees in of a pole shoe by 360-degree. Huh. So if suppose in the previous question, because if we go by this that this is 180-degree per pole, so this 180 by 360 will become 2, which will equal to number of poles P. Okay, but here for this case they are saying that it is the degrees of pole shoe. Instead of taking 180-degree, they are taking now 122-degree. Okay, so how much is the flux per pole? So the flux per pole is pi dl. So here we have pi, we have diameter d in centimeter, so here we have to convert everything into meters, है ना? So this is 5, length is 0.4 into degrees. So degrees are how much? 122 degrees by 360. Okay, so this will give me the flux, this is the area, and into B average. So B average is 0.5. Okay, so this is 0.5. So this will give me the flux. So how much is the flux? Something like 0.095 Weber. You can do the calculation at your home. Okay, now let us go to the next page. So because here it is all crowded. So okay, so here the flux per pole is pi dl into B, degrees of pole shoe by 360. Like this. Okay, so this is the situation. Now this flux we get, so if we put it, we will get flux as 0.0958. Okay, Weber. Now what we need to find? We have to find EMF generated. So we know what is the generated EMF formula. It is ZNP 5 by 60A. So what are the total number of conductors? So you see, as I said, that they have not given directly the number of conductors. Okay, they have given you the number of coils. So number of coils is, they have given as 102, and they're saying each coil has 2 turns. Okay, so we have seen that number of conductors for a multi-turn coil. What is the formula? So number of conductors here for in a multi-turn coil is Z is equal to 2 into T into number of coils, like, right? So let us now see this. So this is what? So this is, so number of coils is, this is because each of the, so this is number of conductors will be 2 into T into number of coils. So this is 2 and number of turns is 2 turns and number of coils is 102. Okay, so this is the number of conductors. So number of conductors is how much? 2 2s are 4, 8, 408, correct. This is 408. Now let us see EG. So what is back? So this generated EMF. So here we have 408 number of conductors. Now speed in RPM is 720 RPM. Then what about number of poles? This is 2. Pi we have calculated. 60. And because this is, you see, lap connected coil, so number of parallel paths are equal to number of poles. So if you simplify this, you will get this as 469.12 volts. Okay. So is there any doubt in this question? Okay. Now we will go to the next question. Now in this next question, we have to estimate the terminal voltage at full load current of 45 ampere. Okay. Now what we need to do is, so this is a generator. Now what generator it is, they have not mentioned. Okay. So has lab. So they have just mentioned a DC generator. They're not mentioning whether it is shunt, series and all. So you can just take it the normal separately excited generator. Okay. So you take it like this. If nothing is mentioned, then you take it a separately excited generator. So they're asking you to find terminal voltage V. So we have the back EMF from the previous, the generated voltage from the previous question. So it was 469.12. Okay. Then armature current also they have given 45 ampere. But what we don't know is we have to calculate armature resistance. Okay. So how to calculate armature resistance? So let us do that. So this is a lap connected coil. So we know what are the total number of conductors Z. 102 into 2 into number of turns. So this is 408. Okay, this is 408. Now, what is the number of conductors per parallel path? Number of parallel paths are 2. Number of poles. So this is 204. Okay. So there are 204 conductors here. There are 204 conductors here. Okay. So this is the situation. Now what we have to find? We have to find what will be the resistances of these two. Okay, so this is R1, this is R2. So what is R1? R1 is, so how we can find out? So you see, so they're saying that each turn has 0.04 ohm resistance. Okay, so what we can do is that we can just, what you say, so here you see these are the number of conductors. Okay, but they're giving the information in the form of number of turns. Okay, so you see that each turn, so in each of the turn is having, this is a 1 turn. So in 1 turn you have 2 conductors. So they are saying that 0.04 ohm for 2 conductors. So each conductor has 0.04 by 2. ठीक है? So 0.02. So here this is 0.02 into 204. Okay, this is R1. So what is the parallel combination of R1 and R2, which is RA? So this is 0.02 into 204 by 2. Okay. So this is how much? So this is 2.04 ohms. Okay. So here we have our RA. So our RA we can write here in this data. So this is what we can calculate the terminal voltage. Okay, so here you see, did you understand that what I did? First, I calculated number of conductors per what you say parallel path. But here they have given the information not per conductor, but they have given the information of resistance per turn. And we know that in one single turn, each turn means one single turn. Now, in each turn, there are two conductors. Okay, so they have given this resistance values for two conductors, 0.04 ohm for two conductors. Okay, so like that. So this is how you can do it. Is this question clear? What about the other Shiv Kumar Mahato? Is this question clear? Okay, so if there is, I hope there is no doubt in this question. Okay, if you have doubt, then you ask in between. Okay, now let us go in the next problem. Now in the next problem, what we have to do is, it is given that this is a DC shunt machine. Okay, so they are saying that this is a DC shunt machine. Now in one case they are operate. So this is the information of a DC shunt machine. So let me just draw it. So here we have the armature and field resistance. So here we have the armature resistance here. We have the field resistance here. And we have the load here. Okay. So this is suppose the case of generator. So they are saying that they are running the same DC machine as the generator. And then they are running the same DC machine as the motor. Okay. So I am drawing the same circuit. Okay. So in one case, the direction of currents are like this. This is EG, this is V, this is RSH, this is RA. नहीं नहीं, वो ये बोल रहा है कि एक सेम मशीन है, एक सेम डीसी मशीन है, उसको हम लोग एक बार जनरेटर जैसा ऑपरेट कर रहे हैं और एक बार मोटर जैसा ऑपरेट कर रहे हैं. ठीक है, तो वो बोल रहा है कि या इन दोनों केसेस में फिर ये रेशियो, इन दोनों के स्पीड का रेशियो क्या होगा. ठीक है, ये बोल रहा है. मतलब सेम मशीन को एक बार जनरेटर जैसे चलाया और एक बार सेम मशीन को ऐसे मोटर जैसा चलाया, तो उन दोनों के स्पीड का रेशियो क्या होगा, वो ये पूछ रहे हैं. ठीक है, सो नाउ लेट अस ट्राई टू फाइंड आउट. So here they have given that the first of all this is a 200 volt machine. So for first case they have given that this is terminal voltage is 200 volt. Okay. So what are the informations they have given? Terminal voltage is 200 volt. Armature resistance is 0.5 ohm. Okay. And your what you say this RSH is 200 ohm. If the machine is connected to a 200 supply, then estimate the ratio of speed as motor to the speed as generator. So for the generator case, what is EG? EG is nothing but V plus IARA. And what about the motor? This is EG is V minus IARA. What is IA in this case? It is ISH plus IL. And in this case, IA is IL minus ISH. Okay. Now, what is ISH? ISH in both the cases is V by RSH. Okay. So this is how much? So this is 200 by 200. because 200 volt V by RSH 200, this is 1 ampere. Okay. So in one case, the IA is, what is the load current? Line current in both the cases is 50. Okay. So in the case of generator, this 51, and in this case it is, in this case 49. Okay. Like this. So now we have to just write these equations. So let us write EG generator and let us write EG motor. Okay. So EG generator is V. What is the terminal voltage V? 200 plus, in this case, IA generator RA. So this is 200 plus, in this case it is 51 into 0.5. So this will come out to be 225.5. Okay. Now what about EG motor? So this is EG motor is 200 minus IA motor RA. This is 200 minus IA, in this case is 49. So this is 175.5. Now what is the so in this case, if you see that what is in both the cases, the flux is proportional to ISH is proportional to V by RSH. So in both the cases, the flux is same. Okay, flux is same in both the case. So what is the ratio of the, so EG is proportional to N into phi. So EG1 by EG2 is equal to N1 phi 1 by N2 phi 2. Now phi 1 phi 2 is same. So the ratio of speeds is nothing but the ratio of the, what you say, this, their EMFs. So they're saying the ratio of speed as motor to speed of generator. Okay. So so this is equal to EGM by EG generator. Okay. By 225.5. Okay, is this question clear? Okay, so this is how you can solve. So this diagram is very important. Okay, then only you will be able to write this KCL and KVL properly. Okay. Now let us go to the next question. Now these next questions are very simple. Now in this question, it is given that the DC generator has 4 poles, 0.04 Weber flux per pole and 240 lap connected conductors, each conductor capable of carrying 20 ampere. The machine is driven at 720 RPM. So first we have to estimate the EMF generated. So we know EMF generated is what? ZNP 5 by 60. So number of conductors is 240. So this is 240. Speed in RPM is what? 720 RPM. Flux per pole is 0.04. Yes, 4. Number of poles is 4. And this is flux per pole is 0.04. Divided by 60 into, what is the number of parallel paths? Because this is a lap connected winding, lap connected armature winding. Okay, so here if you simplify this, you will get this as 115.2 volt. Okay, now let us go to the next question. Now what we have to do, we have to estimate the maximum current deliverable by the machine. So what is the number of conductors per pole? So number of conductors per pole is 240 by 4. So this is how many? 80 conductors per pole. So there are 4 parallel paths like this. Each having 80 conductors. Okay. Now we know that in the series part, each conductor is capable of carrying 20 ampere maximum. So in each of the series part, there will be 20 ampere flowing. Not more than 20 ampere can flow, otherwise the conductor will burn. Okay. So what is the total current at the output? So they're saying maximum current which can be delivered by the machine. So the maximum current which can be delivered by the machine is 20 ampere into 4, 80 amperes. We have seen this in even in the earlier case also, right? When I was discussing this example, so here I was discussing that what will be the maximum current which it can deliver. So I said that it is 4 ampere, right? By adding up these currents in the parallel paths like this. Okay. So here also, this is how we can calculate the maximum current which can be delivered. Now, what about the maximum power? So maximum power is nothing but the current into EMF. So we know the maximum current from the previous question and we know the EMF from question before that. So we can find the maximum power delivered. P max is nothing but EG into IA max. Okay. So EG was 115.2 and IA max was 80. So you can just get the power. Okay. Now it is said that what will be the value of torque which may be required to drive this generator. Okay, so you see, I will discuss this even more in the next class, that torque into omega is power. Okay, so let me write it in the here. So torque into omega. Omega is in radians per second. Okay, this will give you power in watts. So torque has to be in Newton meter. So this into omega in radian per second will give you power. Okay, now what is the relation between this N in RPM to omega in radian per second? Okay, so omega in radian per second is equal to 2 pi n by 60. ओके हाँ, तो तुम्हारा टॉर्क क्या हो जाएगा? टॉर्क इंटू 2 पाई n, जहाँ पे n आरपीएम पे है, बाई 60 इज इक्वल टू पावर. ये मैं थोड़ा सा आई विल डिस्कस दिस मोर इन द नेक्स्ट क्लास. ओके, बिकॉज मोटर विल स्टार्ट एंड देन आई विल डिस्कस मोर, बिकॉज इन मोटर इट इज ऑल अबाउट टॉर्क एंड दिस थिंग, राइट? सो आई विल डिस्कस इट. So here, what is torque? So torque is power by 2 pi n by 60. So power we had from the previous question, power was 9216. So 9216 divided by 2 pi 720 by 60. So correct. Yes. So this will give you something like this. Okay. So that is it for this week. So I discussed many things in this week. So here the most important things are these. Okay, like how to draw these diagrams, how to write the KCL KVLs like this, then only you can solve this week's questions. Okay, then another thing, that what is the number of turns, number of conductors, how their resistance is related, what are the number of parallel paths, all these things. Okay, then this thing also I discussed, how to calculate flux per pole. Okay, like this. And initially I discussed what you say, these all these shunt generator, series generator, motor, how the what you say equations change in the case of motor, how they are in case of generator, like this. Okay, then here I have discussed these things. Then this is the EMF equation which is very commonly used. Okay, so that is all for this week, and this is the lap winding and wave winding various things. Okay, so so we will meet again in the tomorrow in the next week class. So if there is no doubt, then I'll stop the session today here. Okay, if there is any doubt, we will discuss it more in the next class. Okay. Ha. Okay then, so that is it. That is it for today's class. So if there is no doubt, then you can leave. Okay. Okay. Thank you. ठीक है. Thank you, Shiv. So I'm leaving. Okay, Sambit and Shiv, you can also leave. Okay, if you don't have any doubt. Okay. Okay then. Okay. हाँ. Okay. Thank you. हाँ. Thank you.